All right. Good day, everyone. It's so lovely to have you back in my channel. Today, we'll be continuing our conversation of the subject of electrolysis. In my previous class, we dealt with the introduction where I explained in details the mechanism of electrolysis. So if you know you've not watched that video, scroll through my channel, you'll see the introduction to electrolysis. Watch that video before you get into this video for proper understanding. Without wasting time, what are we going to be learning today? We have the highlights on the board. I'm going to be explaining, starting off from classes of electrolytes. Remember, I've explained that the electrolyte is the liquid form of the ionic compound that you are trying to decompose with electricity. Those are your electrolytes. Now, basically, electrolytes are classified into, I would say, two. Some textbooks say three, but I would say two. So we have strong electrolytes and then we have weak electrolytes. Now, what is a strong electrolyte? A strong electrolyte is simply a compound, an ionic compound that dissociates completely when dissolved in water. The word dissociate means separate, meaning when you dissociate such compounds inside water, the ions separate completely in solution. Such electrolytes, we call them what? Strong electrolytes. So examples of strong electrolytes, I will just mention a few. Any strong acid, okay, any strong acid is most likely a strong electrolyte. Every strong base, examples of strong acids, you have hydrochloric acid, you have triazonitrate 5 acid, you have H2SO4. Also, strong bases, examples are sodium hydroxide and potassium hydroxide. And then most ionic salts like sodium chloride, they are actually also strong electrolytes. So I can say most ionic salts of strong acid and strong base. Any salt that is formed from a strong acid and a strong base would most likely be a strong electrolyte, meaning they dissociate completely into their ions in solution. Now, the second class of electrolytes we have weak electrolytes. So weak electrolytes are what? Electrolytes that only dissociate partially in aqueous solution. Meaning when you dissolve these compounds inside water, there would be separation of ions, but the separation of ions is not complete. Not all the components will actually dissociate completely. So we call such electrolytes what? Weak electrolytes. So examples of weak electrolytes, we have weak acids. Weak acids include ethanoic acid. We also have triazocarbonate 4 acid. These are just some examples. Every weak base, for example of a weak base now is aqueous ammonia. Or they write it as NH3.H2O. That's aqueous ammonia. So weak acids and weak base, they are classified under weak what? Electrolytes, because they don't dissociate completely into their ions in solution. We also have non-electrolytes. So non-electrolytes are simply compounds that do not produce ions at all in solution. I mean, if you dissolve such compounds inside solution, ions will not be produced. at all. So examples of non-electrolytes are most organic compounds, okay, just like glucose. Glucose is C6H12O6. Such compounds, they are actually classified as non-electrolytes. So that's that for the classes of electrolytes. Now, talking about conductance of electrolytes, the word conductance simply means the extent or the measure to which a particular electrolyte conducts electricity in the process of electrolysis. So that's what we mean by the conductance. Now, the conductance of electrolytes is directly proportional to what? The concentration of the ions in the solution. What do we mean? Remember that for electrolysis of aqueous salts, meaning from what we learned yesterday, if the salt in our vessel is in the aqueous form, meaning you dissolved it in water, what constitutes current? In our explanation in the last video, what constitutes current? It's actually what? The movement of your hydrated ions. Take note of that. It's a common question asked. So that is one major difference between a metallic conductor and then an electrolyte. Metallic conductors are metals generally, like iron, copper, any metal at all. Metals conduct electricity via the movement of electrons from atom to atom. So if you have a wire, what constitutes the flow of electricity is the movement of electrons from atom to atom. That's what happens for metallic conductors. But for electrolysis, which is for electrolytes, what constitutes the flow of current is actually the movement of these hydrated ions. Just in case you don't know the meaning of hydration, the word hydration or hydrated ions. Now, the solvent contains solvent ions. For water, this water ionizes weakly to OH plus and then OH minus. So by the time you introduce a salt, let's say sodium chloride, in here, sodium chloride has these ions. What happens is what? The ions of the solvent, they surround each ion of your salt by virtue of electrostatic attraction. So it means the hydrogen ion from the solvent would most likely do what? Surround your what now? Your chloride ions, because they are oppositely charged. In like vein, your hydroxide ion that is negative would surround your sodium ion that is positive. This process where the ions of the solvents surrounds or solvates the ions of your salt, that process is what we call hydration. And you should know that, you should take note of it, write it down in your note. Hydration results in the release of energy at the end of the day. Hydration process is an exothermic process because it is a bond breaking process. That is just by the way. So it is the movement of these hydrated ions now, the ions that are now surrounded by water, to their respective electrodes and their subsequent reactions at these electrodes. We learned all this yesterday. Let's say in my last class. So these are your electrode. So these ions, they migrate to their respective electrode. We learned from the previous video when we talked about the mechanism, we learned everything that happens at this electrode. So their subsequent reactions at this electrode is what constitutes the flow of current in the external circuit. So just in case you are asked in your exam for an aqueous electrolyte, the current carriers are dash. The answer to such question is what? Hydrated ions, not electrons, not just ordinary ions, rather hydrated ions. That is by the way. Now, I was talking about conductance. Conductance talked about how well this particular electrolyte conducts electricity in the external circuit. So what determines the conductance is actually the number of ions that are present here. In other words, the concentration of your salt. Concentration has to do with the amount. Meaning if you put a lot of sodium chloride inside your water, meaning you have concentrated sodium chloride, it means you also have a lot of sodium and chloride ions. And the more the sodium and chloride ions, the more the electron exchange that would occur in the circuit. So you should write it down. What determines conductance is actually the concentration of your salt or the concentration of the ions in the solution. It therefore means that what strong electrolytes have high conductivity or conductance. Why? Because in solution they dissociate completely. Whereas weak electrolytes, on the other hand, they will have low conductance or low conductivity. That explains. So we're done with the classes of electrolytes, and also we'll discuss conductance of electrolytes. Now, we'll be moving over to a very important part of this topic, if not one of the most important part of this topic. Preferential discharge of ions during what? Electrolysis. I'll be taking off this part of the board. Give me a minute. Okay, so our board is cleared now. Now let's talk about the preferential discharge of ions during electrolysis. Now, this subject only comes to play when our electrolyte is in the aqueous form. That should be established first. So if our electrolyte is in the melting form, meaning if we melt our electrolyte, we have no business discussing preferential discharge of ions. But when our electrolytes, I'm going to draw a diagram for us to understand. So this is your electrolyte, and these are your electrode dipping into the electrolyte. Okay, this means to be a battery rather. All right, so if this is the positive end of our battery and this is the negative end, this will be the positive end. This is the positive electrode. These are negative electrode. For this part, we said these are anode for the electrochemical cell, while this is our cathode for the electrochemical cell. So you have your anode and then you have your cathode. Now, for an electrolytic cell, this becomes your cathode. We've explained all this in the previous video, and this becomes your anode. All right. Now, if our electrolyte is in the aqueous form, it means that the ions here would be, let's imagine we have an aqueous solution of sodium chloride. If we have an aqueous solution of sodium chloride, in solution, we have our sodium ion, we have our chloride ion. In the same vein, we have our hydrogen ion, and then our hydroxide ion. So we have all these ions. These are gotten from the solvent. Remember, water ionizes weakly to these ions. So during electrolysis, when you put on your battery, from what we learned in our previous video, the positive ions in the solution would migrate to the negative electrode. So sodium and hydrogen would migrate to this electrode. And only one of them would be discharged at the end of the day. In like vein, your hydroxide ion, which is negatively charged, will migrate to the anode, which is positive. Then your chloride ion also will migrate. Let me just draw this. So your chloride ion also migrates to this particular electrode. Now, we have two electrodes, we have two ions rather, migrating to both electrodes. And when they get there, they compete for who would be preferentially discharged. Meaning that when sodium and hydrogen moves this way, Remember, electrons come from the anode of your battery down to your cathode over here. So when sodium and hydrogen moves to this electrode, they would fight and they will compete with themselves for who would actually be receiving the electrons being pumped by the battery. The same thing happens for the case of hydroxide and chlorine. They both migrate to this electrode where they compete for who would lose electron. Remember, at this electrode, which is your anode, that is where oxidation occurs. Oxidation will occur here. Then at the cathode, you have reduction occurring here. We said all this in our previous video. So it means reduction refers to loss of electron, reduction refers to gain of electron, oxidation refers to what? Loss of electron. Now, when sodium and hydrogen migrate here, they would compete for who would actually lose electron. There are three factors that now determines which of those ions would be preferentially discharged. So the three factors that determine the preferential discharge of ions during electrolysis are one, and we're going to talk about the position of ions in the electrochemical series. All right. Now, the first thing you do in your exam for you to determine what is being discharged at any of the electrode is to compare the position of the two ions competing in the electrochemical series. Just in case you don't know what the electrochemical series is, the electrochemical series is simply a series that shows the arrangement of elements in order of their electrode potential value. We learned about electrode potential in the previous class, where we say electrode potential is the tendency of a metal to either lose or gain electrons when in contact with a solution containing its ion. Some persons define the electrochemical series as a series that shows the reactivity of elements. So there's a limitation to that definition anyway. So I'll be giving you the electrochemical series for both metals and then non-metals in the next slide of the board. So I will need to get rid of what we have here. All right, so I've taken my time to write out the electrochemical series for both metals and non-metals. All right, now you should take note that there is a twist in these two positions. Okay, so what I actually wrote here in more practical sense is actually your activity series, your reactivity series, which is very similar to the electrochemical series aside these two positions. So in the electrochemicals, in the activity series, sodium is more reactive than calcium. But if you are to arrange them in terms of their electrode potential, which is the electrochemical series, calcium ought to actually come first before sodium. That's just by the way. It's not a big deal. All right. So I've given you a learning aid you could use to remember for both the metals and then the non-metals. But you need to understand something about the electrochemical series or the activity series. Generally, as you are moving down the series, okay, as you're moving down the series for the metals, your reactivity decreases. So you should take note of that. So it means in this series, potassium is the most reactive metal according to this series compared to every other. So as you're going down, you're moving from the good metals down to the inert metals. So gold is very inert. That's why you can find gold in the uncombined form in the earth crust, because it doesn't react that much with moisture or oxygen in its environment. So that is for the metals. You could use the learning aids to remember them. Learning aid says, please stop calling me a zebra. I truly like her calling me super powerful giraffe. Then for the non-metals, you have your learning aid to be, he's becoming contagious now, so flee. So you use that to remember these are the ionic symbols. Now you should take note that what happens here is the opposite of what happens here. So it means as you are going down, you are actually moving towards the more reactive non-metal. So it means the most reactive non-metal, as far as chemistry is concerned, is fluorine. So that's what we should take note of. So remember that metals want to exist, good metals and good good non-metals would want to remain as ions. That should be one point you should remember. So if we have a competition between, from what we're saying here, hydrogen and sodium, the first point of concern is their position in the electrochemical series. That's the first factor we're discussing. So sodium is up here in the series, hydrogen is down here in the series. That tells us that sodium is a better metal than hydrogen. And remember, better metals would want to stay in solution as ions because they love releasing their electrons. So it's not feasible for sodium to accept electron from this anode. Why would you not want to accept electron? Because sodium is a good metal. It would prefer to remain this way in solution. So it therefore means that in the competition between sodium and hydrogen, hydrogen being a poor metal, meaning a metal that doesn't really want to exist as ion, would be the one that would be preferentially discharged. So hydrogen gets the electron coming and it becomes discharged as neutral atoms. So that is what happens here. Now let's talk about the non-metals. When hydroxide and the chloride ion move here, the first thing you should check in your exam, if I should ask you what is formed at the anode in the electrolysis of aqueous sodium chloride using platinum electrode. Now, this is one thing I would say, please take note. Platinum electrode or graphite electrode, graphite is an allotrope of carbon. These two electrodes, when you see them in your exam, they are actually called inert electrode. Inert electrodes, the spelling is inert. Inert electrodes are electrodes that do not interfere with the electrolysis process. As you can see, platinum is an inert metal. It's down here in the electrochemical series. So when you're using platinum as your electrode, you should know that it's not going to interfere with the products of your electrolysis. That's just by the way. Now, when hydroxide ion and chloride ion migrate here, the first thing you check is your electrochemical series for anions, now for non-metals. So remember I said for non-metals, as you are going down, reactivity increases. It means chlorine, look at the position of chlorine and then look at the position of hydroxide. It means chlorine is a better non-metal now. Chloride ion is a better non-metal now compared to the hydroxide ion. So it means that what? The chloride ion would prefer to remain in the solution as chloride ion. While the hydroxide ion, which is relatively the, in quote, poor non-metal in this case, would do what? Would want to be discharged as neutral atoms. So hydroxide ion would release its electron out here to this electrode and the electron flows out to the external circuit. So let me summarize what I have said. Key point is this. When you want to determine the product of whatever is formed on the cathode or anode, the first thing you check is the position of the ions competing in the electrochemical series. For the positive ions, a positive ion that is down the series will most likely be what? Preferentially discharged compared to the one that is up here in the series. That's for the cations. Now, for the anions, for non-metals, an anion that is up in the series, in the case of hydroxide now and chlorine, an anion that is up here in the series will most likely be discharged compared to an anion that is down here in the series. So I have just dealt with the first factor that determines what? The preferential discharge of ions during electrolysis. And the first factor, which is one of the most important, in fact the most important, is the position of the ions in the electrochemical series. Now we're going to the second factor now, which is the concentration of the ions in the solution. All right, so we've established that the first factor we look at when we are determining which ion would be preferentially discharged at any of the electrode is to compare those two competing ions to compare their positions in the what? Electrochemical series, which we've done in the previous section. Now, let's look at the second factor now. The second thing you look at, the concentration of the ions, or let's say the concentration of the salt. Now, what do we mean by concentration? Concentration simply means amount. So it means if you put a lot, generally, okay, if you put a lot of salt in your solution, in your solvent, meaning if the amount of salt in this solution is much, all things being equal, it tends to promote the discharge of the ions of that salt. But then there's something you must always remember. The effect of concentration is only considered if those two competing ions are close to each other in the electrochemical series. So if the two ions are very close to each other in the electrochemical series, that is only when I would consider the effect of what? Concentration. For instance, let's imagine we are to carry out electrolysis on copper 2 tetraoxosulphate 6 in the aqueous form, concentrated form of this, meaning if I put a lot of this salt in water, let's consider what will actually happen. Now, in the solution, let's focus on the metal, which is the ions that would move to the cathode. The cations in this setup are going to be Cu2 plus, which is the ion gotten from the salt, and H plus, which is the ion from the solvent water. Now these are the two ions that would be competing. So under normal circumstances, we all know that what copper is below what? Hydrogen in the electrochemical series. So looking at position in the electrochemical series, copper will be preferentially discharged, obviously. And then if this salt is now concentrated, in fact, it promotes the discharge of copper more compared to, it means the amount of copper that will be discharged in this case would be more than the amount that would have been discharged if the solution was a dilute solution. So we're going to discuss the types of electrolysis in a short while. All these factors will be put into place when we'll be determining the products that will be formed at each of the electrode. So the concentration of the salt only comes to play, like I've said, if the two ions that are competing are very close to each other. Just imagine a competition between hydroxide ion, which is the ion in the solvent. Let's just imagine there's a competition between hydroxide ion versus let's say iodine ion, for instance. So iodine ion and hydroxide ion are actually close in the electrochemical series. So if the salt that is producing this iodine ion is if the solution is concentrated, it therefore means that what? In that case, instead of hydroxide to be preferentially discharged, it's iodine that would be preferentially discharged. Why? Because iodine and hydroxide are close to each other in the electrochemical series for what? For non-metals. But if the ions that you are comparing are far apart, you don't consider the effect of what? Of concentration. That is that for concentration. Now, the third factor that we look at when we're trying to determine what would be preferentially discharged is the nature of the electrode we're making use of. Nature of electrodes. So, the type of electrodes you use determine what happens in the electrolysis process. If you are making use of inert electrode, I'll explain what inert electrode are. For example, graphite, which is carbon electrode, or platinum electrode. These electrodes don't actually interfere with the product of the electrolysis. But then, let's imagine we're carrying out this particular electrolysis and let's say we make use of mercury as our anode. Let's just bring this down. We make use of mercury as our anode. Let's see what will happen in this situation. If you make use of mercury as your anode, normally we know that the ions that migrate to the anode are what? Your chloride ion and your hydroxide ion. But if you make use of mercury as your anode, what happens? Remember, at the anode, oxidation would occur. So mercury is a metallic atom, meaning by default, metals are wired to always lose electrons. That we should understand. So when hydroxide and chloride ion migrate to this particular electrode, none of them in this case would be discharged. Rather, mercury atoms in here would be the ones to carry out the oxidation process. Why? Because mercury is a metal. So it takes less energy for metals, for mercury atom to lose its electron than for these negative ions to lose their electron. So making use of mercury as the anode will not promote the discharge of any of these ions. Rather, mercury atoms here will lose their electrons and then come into the solution as what now? As ions. So it therefore means that if you are carrying out this electrolysis, it's a common question that you will be asked. One of the products, this vessel at the end of the day, if you should carry out analysis on this vessel, it would contain some impurities of what now? Mercury chloride at the end of the day. Yes. So in case you should see a question like that, in the electrolysis of sodium chloride, making use of mercury as your anode, one impurity or something that can be found on this vessel at the end of the reaction is what? Mercury chloride. Because this and this can now bond together. Since they are oppositely charged, they can bond together to give you mercury chloride as an impurity, small amount of what? Impurity. So this is what happens. Just because we changed the anode from platinum to, let's say, mercury, it's prevented the what? The discharge of what? Your hydroxide ion. Let's look at another case where the nature of electrode affects the product that is formed in electrolysis. Let's look at the second case. Now, in the electrolysis of copper 2 tetraoxosulphate 6, pay attention. In the electrolysis of copper 2 tetraoxosulphate 6, I need the board white, please. Okay, so we have a diagram of the electrolysis of copper 2 tetraoxosulphate 6. Now, let's look at what happens. Remember, we're still discussing what? The nature of electrodes. I've explained the case of this when you make use of mercury as your anode. Now, let's discuss the electrolysis of copper 2 tetraoxosulphate 6. If we should make use of copper, now let's look at what will happen. If you are making use of copper as your anode, the cathode can be platinum. We always know that at this part, what would be preferentially discharged in this case is what? The metal that is down in the electrochemical series. So hydrogen will be discharged at this particular electrode. That is established. Now, for the anode, if I am making use of copper, if I were to make use of a platinum electrode normally, we should know that hydroxide ion will be what would be preferentially discharged. Take note of that. But if you make use of copper anode, remember we learned in the previous video that whenever you have a metal dipped in a solution that contains its own ion, this solution contains copper ions now. So because this electrode you are using have a relationship with an ion inside this solution, it promotes what? The oxidation of the copper atoms here. So the same thing that happened in the case of when we make use of mercury as this anode, the same thing happens here now. So instead of the anions to actually compete, and which we know hydroxide would be discharged, because copper is in contact with a solution that contains copper ions, what happens now? The copper atoms that are here now fall into the solution now as what? As ions. So the copper atoms here will lose their electrons and the electrons will flow out. And then they come into this solution now as what? As ions. They fall into the solution as what? As ions. So at the end of the day, you would notice that the next process that is occurring in this place is what now? Your copper atoms now are just falling out into the solution, thereby increasing what? The concentration of copper ions in the solution. I believe this is super clear. Yes. So we have discussed two cases where nature of electrodes affects the product of electrolysis. If you should make use of platinum electrode in the electrolysis of aqueous sodium chloride, we said hydroxide ion will be preferentially what? Discharged. But if you should make use of mercury as your anode, instead of hydroxide being discharged, mercury would now be discharged. Since it's a metal and it has a higher tendency of losing electron, mercury atoms will lose electron and fall into the solution as ions. Another reason why mercury would even want to even do this is because there is a very strong association that exists between mercury and sodium. Mercury and sodium forms an alloy we call amalgam. So that alone promotes the oxidation of mercury to ions in the solution. So these are the three factors that affect what will be discharged at the respective electrode. The position of the ions that are competing, the concentration of each of the ions, and then the nature of the electrodes that you make use of. So if you don't want your electrode to affect the products of your electrolysis, you make use of inert electrodes, such as what? Platinum and carbon. I believe this section is very clear. Now, lastly for today, or second to last, we'll be going into what now? Examples of electrolysis, that questions that are usually asked, some compounds that are asked in your exams. We're going to discuss the electrolysis of brine, we're going to discuss the electrolysis of acidified water, and then we'll discuss the electrolysis of copper 2 tetraoxosulphate 6. Let's watch. Okay. So now let's look at some examples of what? Electrolysis. So the first electrolysis we're going to be discussing is the electrolysis of what? Acidified water. It's also known as the electrolysis of dilute tetraoxosulphate 6 acid. Meaning if you place small amount of tetraoxosulphate 6 acid in water, you have dilute tetraoxosulphate 6 acid. What happens when we carry out electrolysis on that particular compound? Here we are going to be making use of platinum electrode or carbon electrode, which are what? Inert electrode, meaning what? That they don't interfere with the reaction. Now, you could just do yourself good by just taking note of this, that for the electrochemical series for non-metals, okay, XO4 is down in the series. So most times in electrolysis, the hydroxide ion is always being discharged, since it is actually the first ion that occurs in the what? Electrochemical series for non-metal. So you just put in your head that for whenever you are doing comparison for your anions, your hydroxide ion would always be discharged at the end of the day. That should be taken note of. And then hydrogen being down in the electrochemical series for metals. Remember, for metals, those ions that are down would be preferentially discharged. So hydrogen being down the electrochemical series would be preferentially what? Discharged. We should take note of that. Now, having said all of this, without drawing the diagrams, we're just going to be discussing what would happen at the anode. So I'll write at the anode. Remember, your anode is what? The positive what? Electrode. Remember, where oxidation occurs. So let me just include it at the anode. That is where your oxidation occurs here. So the anode is that electrode that what? The anions would move to. So the anode is actually the positive electrode. Positive electrode. So if the anode is a positive electrode, it means what? The negatively charged ions will be moving to the anode, just like the name anions, anode ions. Anions are the negatively charged ions. And if you should dissolve this in water, what would be the ions present in your exam? Just list out the ions. First of all, I have H plus ion present. Even the solvent has H plus. The acid also have H plus. And then we also have OH minus from the solvent. This is for the solvent. We have 2H plus. This is solvent. Then we have 2H plus, and then we have SO4 2 minus. So these are the ions from your acid. So list out the ions as a guide in your exam. So if we're looking at the anode, remember the anode is the electrode where the anions, these are the anions that will migrate to this anode. And I've just told you that the hydroxide ion is always being discharged in most cases. So it means in this, the hydroxide ion will be preferentially discharged compared to this, since this is higher up in the electrochemical series for non-metals. So what would happen there? Your hydroxide ion, OH minus, oxidation means loss of electron. We lose one electron corresponding to the 1 here. Hydroxide is the valency of hydroxide here is 1 minus. So it will have to lose 1 electron to become neutral OH. But this is not a substance, as we can see. This cannot exist. Why can it not exist? Because the valency of oxygen would not actually be satisfied in this case. So what happens? This process would occur again to produce, so this occurs again to produce another OH. When this OH is now produced, another new OH is produced, the two OH, they combine together to give you H2O, which is H plus H gives you H2, then O, then you are left with one oxygen atom over here. So this is water. Also, in chemistry, oxygen cannot exist in this atomic form. So the reaction at the anode cannot end here. So this whole process that I have done now, we have to occur again. Why? To produce another free atomic oxygen. So the second atomic oxygen that will be produced combines with this first one to give you oxygen gas. So it means the product that is actually formed, the next product, there are two products now if you look at it, water and oxygen. But water cannot really be seen as a product in that sense because in the reaction system, we already have water. So the only new product that is formed in this reaction is what? Oxygen gas. So if you are asked, in the electrolysis of acidified water, what is produced at the anode? The answer is what? Oxygen gas. And this is how you derive your answer. I believe this is clear. Now, if we are to write our overall equation here, overall anodic equation, anodic reaction, meaning if I want to write everything that happened here, we are to write it in a single line. Let's summarize it. So in total, we have 4OH minus. Why? Remember, initially you multiplied this equation by 2, so you have 2OH minus. Then later you multiplied everything again by 2. 2 times 2 now gives you 4. So you have 4 hydroxide ion would lose a total of 4 electrons. Okay? To give us, what are the products at the end of the day? You are writing the ideal products, which are what now? H2O and oxygen gas. So this is your overall equation. But don't remember from the previous class, I told you in chemistry, we don't leave our equations having negative sign. So we take this over to the other parts of the equation. So we write it as plus over here, plus 4E minus. So this is your overall equation, that is your overall reaction that is occurring at the what now? At the anode. So you can check if this equation is balanced. We have 4 oxygen atoms here. Obviously, it is not balanced. That's the next thing you should check. Why is it not balanced now? Remember, you multiply the whole process by 2. There's a 2 here. So it means even this water now would be multiplied by 2. So the number at the back of this is what? Is 2. So if you count it now, you have 4 hydrogen, you have 4 hydrogen, you have 4 oxygen, you have 2 oxygen plus this 2 oxygen will give you 4 oxygen. You have 4 negative species over here, you have 4 negative species over here. So both the atoms and the charges are what? Are balanced. So this is the net reaction that occurs at the what? At the anode. Now let's look at what happens at the cathode. So at the, I'm putting this off. So we'll say at the cathode now. Let's see what will happen. At the cathode, what occurs at the cathode, remember, is reduction. Reduction occurs at the cathode. So the cathode is that electrode where what? Your cations would move to. These are the cations. Are they different? No. So it's just hydrogen. So there's no competition occurring there to even start with. So we know that hydrogen ion just needs 1 electron to become deposited as neutral hydrogen. So hydrogen ion would collect. Why am I saying plus? Because reduction is gain. So this ion would gain 1 electron to become neutral hydrogen atom. But hydrogen does not exist as an atom, remember. So what do? This process occurs twice. So it occurs again to produce another hydrogen. So the free hydrogen that is produced, we combine with the previous hydrogen to give you hydrogen gas at the end of the day. All together. So if you look at this explanation now, it means the total electron that is involved in this process is just 2 electrons. Because if I use this 2 to multiply this, I have just 2 electrons. But then, from what we discovered in the oxidation process, a total of 4 electrons were lost. So the number of electrons lost must be equal to the number of electrons gained. But from this now, I have just 2 electrons being gained here now. So we can't possibly end it here. So what do I do to balance it up? I multiply this whole process by 2 again. So if I should do that, I will come down and write my overall cathodic reaction becomes what now? The overall cathodic reaction becomes a total of, if you look at this, I used 2 to multiply here before, I used 2 to multiply again, so I have a total of 4 hydrogen ions, as we can see, would accept a total of 4 electrons to give you, if you are multiplying this by 2, remember, you have 2 hydrogen gas. So this is what happens at the what now? At the cathode. Now, for you to get your overall cell reaction, I've shown you how to do this. Overall cell reaction. Overall cell reaction. What you simply do now is to combine this overall reaction for the cathode to the overall reaction for the anode. So if we combine these two, you get your final answer. By the time you combine it, this 4 electron in the reactant side will cancel this 4 electron in the product side. So what will be left now becomes what? You start from this. You have 4 OH minus. Okay, you come to the reactant here, plus 4H plus to give you, the electrons have cancelled out, so there's no electron there. You go to the product here, you have 2H2O, then plus O2, then plus, you come to the product here, you have 2H2. So this becomes your answer. So from this, for your exam, you should just take note of this, that at the anode, the main product there is oxygen gas. Then at the cathode, the main product there is what? Hydrogen gas. We are going to move to the second example of electrolysis now. Okay, now let's look at the second example of electrolysis, which is the electrolysis of copper 2 tetraoxosulphate 6 using different electrolytes. So firstly, we're going to use an inert electrolyte, let's say platinum or carbon, which is graphite. Take note, the allotrope of carbon that conducts electricity is graphite, okay? So in case you see it in your exam, graphite is an inert electrode. It does not interfere with the electrolysis process. That said, remember I said when you are trying to determine the products at the anode and cathode in your exam, what you do is list out your ions for both the solvent. So I'm going to list them out. For my solvent, you already know the ions in your solvent are OH minus and then H plus. Then your ions for your salt are, the salt here is copper 2 tetraoxosulphate 6, which is the formula is CuSO4. Okay, so the ions there would be Cu and then SO4 2 minus. So we have SO4 2 minus, we have Cu2 plus. Those are the ions present. So you first of all list out the ions. So let's start off with the anode. So using at the anode now, I at the anode. Remember what happens at the anode is oxidation. Oxidation occurs, loss of electrons. So the anode is that electrode where what the anions would move to. So these are the anions, this and this. So these two ions will move there. And as I've always said, OH minus is always what? Preferentially what? Discharged. So your OH minus, we've already done this before. I don't need to repeat it. It's the same thing with the previous example. We ended up deriving that at the anode, whenever OH minus is being discharged, just put it in your head. What happens is what? 4 OH minus would actually lose 4 electrons to give you 2 moles of water and oxygen gas. So this is the reaction. I've shown you how to get this reaction in the previous example we did, all right? So this is what happens at the anode. OH will be preferentially discharged. Now let's look at what happens at the cathode. At the cathode, which is where reduction occurs. So at the cathode, what are the two ions going to compete? Hydrogen ion and Cu2 plus ion. So out of the factors that determine who will be preferentially discharged, we're making use of what? The electrochemical what? Series. Okay, so remember for the cations, a cation that is down in the series will be preferentially what? Discharged compared to another that is up in the series. So in the electrochemical series, copper is down, it's under hydrogen. So it means copper would be preferentially discharged. So it means at the cathode, you have Cu2 plus. Okay, reduction means gain. So you gain 2 electrons to become discharged as what? Copper atom. But just like what I said in the previous example, the total number of electrons lost here is 4 electrons. So the total number of electrons that should be gained here should be 4. So to make that happen, I multiply this equation by 2. So it therefore means that what would happen there is we have 2 copper ions would receive 2 times 2 is 4 electrons to produce 2 copper atoms. So I use 2 to multiply all through to make the number of electrons equal. So they must be equal. So this is the reaction that occurs at the what? At the cathode. So it means in the electrolysis of what? Copper 2 tetraoxosulphate 6, making use of platinum electrode, the products are what? Oxygen at the anode and then copper at the cathode. So let's write our overall cell equation or reaction. So our overall reaction, remember for you to get your overall reaction, you are adding the final answer here to your final answer here. So you start with the reactant side. We have 4 hydroxide ion. Okay, we have 4 hydroxide ion. Come to the reactant part of this, plus 2 Cu2 plus. Remember, I told you once the electrons are not the same, they cancel out, so you have no business with that. So what you have here now is what? 2 H2O, then plus O2. So the product you have here in this case is 2Cu. So this is the overall reaction that occurs at the what? At the electrolytic cell. I believe this is clear. Now let's look at the electrolysis of this same compound using copper as the anode. Let's see what will happen in that case. All right. So we just discussed what? The electrolysis of what? Copper 2 tetraoxosulphate 6 using platinum electrode. So in what we did, these are the ions of the solvent, these are the ions of the salt. Okay, let's start with SO42 minus and then Cu2 plus. So at the end of the day, we said that hydroxide ion was discharged at the anode. That's what we said. And also we said what? Copper ions now was discharged at the cathode. That's what we just learned, isn't it? So it therefore means that in our solution, what is left inside our electrolytic cell now is just what? Hydrogen ion and SO42 minus. And these two can actually combine now. They can combine with each other to give you H2SO4. So it means that as the electrolysis progresses, in the electrolysis of this compound using platinum, as the electrolysis progresses, what happens? The solution becomes more and more what? Acidic. So if you should put a litmus in this solution, it's a common question in your exam, JAMB and WAEC. If you put a litmus in this solution, what do you think will happen? So I wouldn't tell you that. What happens to litmus when litmus comes in contact with an acid? Does it change from blue to red, or does it change from red to blue? Find that out. But it's a common question. So take note that the solution becomes more and more acidic. So if you continue with this electrolysis, by the time all the copper ions and all the hydroxide ions have left, and you still continue with the electrolysis, what you will now be carrying out is now the electrolysis of what? Dilute tetraoxosulphate 6 acid. That is just by the way. Now let's look at what happens if we should make use of using copper anode. Using copper anode. Let's look at what will happen. So the cathode remains the same. Whatever I explained for the cathode still remains the same. But let's look at what happens here now. So I at the anode. We're making use of copper as the anode, remember. Now, from what we learned, we said that whenever copper now is in contact with a solution that contains its ion, that solution will contain copper ion, remember. So instead of, remember, these two ions are supposed to come down to the anode, which is OH minus and SO4 are supposed to be the ones competing. But I have explained to you that if you should make use of copper as the anode, what happens is what? The copper atoms in the anode will be the one to actually now lose electrons and enter into the solution. We've already explained that before. So it means in this scenario, neither OH or SO4 would be discharged. So what happens at the anode now is what? The copper atoms, right, in the rod will do what now? Will lose 2 electrons and then change to copper ions and enter into the aqueous solution. This is exactly what happens in this case. So the copper atoms in the rod lose their electrons, fall into the solution as ions. So this is your oxidation process. All right. And you know, as usual, what happens at the cathode? The same reaction that occurs before, which is your reduction, is the same reaction that would occur now. So at the cathode, remember the copper ions that are inside the solution would accept 2 electrons, reduction is gained, to give you copper solid. So what do you notice in this process? It therefore means that if you should make use of copper as the anode, what is essentially happening here is what? Transfer of what now? Copper from the anode to the cathode. This is your cell. I don't need to draw the full cell. just for you to understand. Okay, so this is your, let's say, this is your positive electrode, this is your negative electrode. So this is your cathode, and this is your anode. So in the solution, we have Cu2 plus. In the solution, we also have hydrogen ion in the solution. We have hydroxide ion. We have SO4 2 minus ion. Now we are saying that at the anode, at this particular anode, which is copper now, the copper atoms here will lose electrons, will leave their 2 electrons here, and they will flow out of the wire and then fall inside the solution as Cu2 plus. This Cu2 plus, remember, positive ions will migrate to this particular cathode where they will be discharged at the cathode, as we can see. So it therefore means that as time is progressing, nothing is happening to the composition of this electrolyte. Nothing happens. Nothing is happening to the OH minus, nothing is happening to the SO4, nothing is happening to this Cu2 plus, nothing is happening to this H plus. So we are simply transferring copper atoms from the anode to the cathode. So the composition of this, your electrolyte, remains the same in this case. Nothing changes. You should take note of that. In the other case, where we use platinum electrode, if we should make use of platinum here, we said what now? Your copper atoms will. So I have established now that in this case, what happens is what? The copper atoms here are just being transferred from here to the solution, from the solution to this part. So nothing happens to the original ions in the solution. Questions will be asked in that regard. So now we're going to go to our third electrolysis. We'll take up what we have on the board. Okay, now we'll be looking at this last example of electrolysis. It will end this video. We're going to continue in our subsequent videos. Now we're going to look at the electrolysis of concentrated sodium chloride, which is also called the electrolysis of brine. Concentrated sodium chloride is also known as brine, just in case you see it in your exam. So we're going to discuss what happens at the anode. So at the anode, where oxidation occurs, remember, in this case, in industries, the anode made use of here is platinum. Okay? Platinum electrode. That's what we're using. Meaning it does not actually interfere with whatever is going to happen. So that's why we chose this. So let's look at what happens. Remember, if you are carrying out electrolysis, list out your ions. So let's list out our ions. We have sodium chloride made up of sodium ion and chloride ion. The solvent, water, is made up of hydrogen ion and hydroxide ion. So the anode is that electrode where these anions would move to. So chlorine and hydroxide will migrate there. Now, working with the rule of the position in the electrochemical series, we've always said that hydroxide ion would be preferentially discharged. But then there is a twist because we are looking at concentrated sodium chloride. If you look at the position of Cl minus and OH minus in the electrochemical series for nonmetals, those two positions, they are close. The two ions are close in the electrochemical series. So the effect of concentration will come into play here. So it means that in this case, the chloride ion is more concentrated than what? The hydroxide ion. So instead of hydroxide ion, which we know to be preferentially discharged, the chloride ion will be preferentially discharged in this case. Why? Simply because it is more concentrated. The effect of concentration come into play here. So what happens is what? The chloride ion will lose electrons to become chlorine atoms. This is your equation. But chlorine is a diatomic gas. It does not exist in the atomic form. So this process have to occur again. And when it occurs, what happens? You now have 2Cl minus to give you chlorine gas, which is Cl2 gas plus 2 electrons. So this is what happens at the anode. So if in case you are asked what is the product formed at the anode in the electrolysis of brine, the product is chlorine gas. Take note of that. Then we look at what happens at the cathode. The cathode is your reduction site, remember. Gain of electrons will occur there. Now, what do we use as the cathode? In this case, we are going to be making use of a layer of mercury. A layer of mercury is being used as the cathode. Now, remember the cathode is that electrode where your cations will migrate to. Are you there? Okay. All right. Power has been broken. Nigeria. So let's continue. So we said at the cathode, we're going to be making use of what? A layer of what? Mercury as our cathode. The cathode is the electrode where these two guys will migrate to, and when they go there, one will be preferentially what? Discharged. In this case, which of them will be preferentially discharged? None of them actually will be discharged. The question is why? But hydrogen is down there in the electrochemical series. Hydrogen is supposed to be discharged actually. The distance between sodium and hydrogen in the electrochemical series for metals is large. So the effect of concentration is not felt there. You don't consider concentration. So ideally hydrogen, if we are making use of a platinum cathode, take note in case you are asked. If your cathode is platinum, the product would have been hydrogen gas. Hydrogen would have been preferentially discharged. But because we are making use of a layer of mercury, what happens? We've already learned that what? Mercury will form a loose association with what? With sodium to form amalgam. There's a relationship between those two ions. So what happens is what? The mercury in the cathode, those atoms, will do what? Lose electrons. I will get into the twist of what is happening now. So the mercury would actually what? Be the one to rather, okay, I've gotten water. So what we're saying now is what? In the case of sodium and hydrogen, what happens is because we're making use of mercury as our cathode, the mercury will bond with the sodium to form amalgam. That's the first thing that happens. So sodium and mercury would bond. So you're going to have an association between sodium and mercury. We'll write it this way. This is what happens. So your sodium and mercury bonds together to form a loose association. All together. So this loose association is a loose association because they can easily be separated by what? Hydrolysis. So in summary, this is what we're going to have. Let me just summarize the next process here. The amalgam that is formed, which is Na/Hg, a loose association, when hydrolyzed, meaning when you react this with water, the amalgam will break down to sodium hydroxide and hydrogen, and also we have back our mercury layer, which is liquid. So you have hydrogen gas, this is aqueous, this is liquid. So this is the next process that will occur in the industry. This is what actually happens. So I repeat, the mercury layer in the cathode forms a loose association. This is what we call amalgam. But this loose association that will be formed at the cathode is a weak association. So it can easily be broken down when you hydrolyze. When you wash this with water, it breaks down to sodium hydroxide, hydrogen gas, and then what? Mercury liquid. The mercury liquid in the layer will be formed again. That's why we call this a loose association. So the products that are formed during the electrolysis of concentrated sodium chloride are: one, chlorine gas at the anode. That we are making use of platinum electrode. Two, sodium hydroxide and hydrogen gas. That is, if you are using a layer of mercury as your what? As your cathode. Please, that should be noted. However, if you make use of platinum electrode here in your exam, if the cathode is platinum electrode, what would have been discharged is what? Is hydrogen ion. So the product would have been just hydrogen gas and chlorine gas. For emphasis sake, I repeat, if both electrodes used are platinum electrode, what will be formed? The products will be what? Chlorine gas and just hydrogen gas. But if you are making use of platinum electrode at the anode and then mercury as the cathode, the product becomes chlorine gas, sodium hydroxide, and then you also have your hydrogen gas. So we're going to cut the video here. The next video, we're going to be talking about Faraday's laws of electrolysis. We're going to be solving a lot of calculations on that. And lastly, we then discuss the uses of electrolysis. Thanks for sticking around for this lengthy video. I'll see you in my next class. Please share this video, like, comment, and please subscribe. This is the only way you can support this channel. Thank you very much.